everyone, my name is Balaj. Welcome to episode 3 of the KZ440 EV Restomod. On today's video, we'll be looking at the entire EV drivetrain. So everything from selecting the cells to building the battery pack and then connecting and configuring the charger and the motor controller to make the entire thing work. So because I want to make this bike road legal and registrable, the very first thing I did before starting any of the electrical design work was to look at VSB 14, which is the Australian Vehicle Standards Bulletin for EV conversions. Now this document goes into a huge amount of detail on exactly what you need to do for an EV conversion, and it covers everything from low voltage and high voltage isolation requirements through to wiring safety and wiring colors, as well as battery safety. The first thing I needed to do was to pick the motor, because this would have a pretty big influence on the battery capacity and the motor controller that would be needed. I'd seen a lot of other bikes online using this 8 kilowatt QS motor hub drive, and they were getting some pretty great results. And since this was my first EV build, I wanted something that would be relatively straightforward to get going. The Kelly Controller 8080i motor controller was chosen for the build because this model has isolated high and low voltage sections. This level of isolation was one of the requirements in VSB 14 that's needed for registration. The next step was to size the battery and look at what alternatives were available. I made a really rough power model that helped visualize the power draw at different speeds. This was a way to work out roughly what capacity would be somewhat functional for a daily rider. I was originally looking at making the battery pack out of 18650 cells, but a 24 series by 20 parallel pack would have needed about 480 cells, and it was difficult to get these in the capacity and discharge rating I needed without blowing the budget. I found a really great value Lithium NMC pouch cell with a capacity of 74 amp hours, which is rated at 2C continuous discharge or 148 amps. So these LiPo cells are typically considered more volatile than the 18650s, but they're used pretty commonly in laptops and phones, and we don't see those exploding every day. So the key to making sure these operate safely is to tightly control the charge rate as well as the maximum voltage and the discharge rate and the voltage floor. I wanted to test the stability of the cells by seeing just how much overcharging was needed to cause failure. The cell was initially connected to a lithium specific charger on the 4.3 volt high power profile. It ran for most of the day without any noticeable temperature increase. I was fairly happy with the overall performance at this point and decided to move on to the real test. I connected an 800 watt 12 volt power supply to accelerate the action. The battery stood up to over 3 hours of this before expanding, popping and then exploding. I stopped several times through this process to measure the cell voltage, and from what I could tell, the pouch only started to expand after it was fully charged. To be honest, this wasn't really necessary. I just wanted to see an explosion. But it is a really good demonstration of why tight control over the charge rate and maximum charge voltage is really important at a cell level, and a capable battery management system is an absolute must when running these in series. I spent a few weeks researching charger options and ended up coming across this beast from Thunderstruck motors. It was actually the finned housing design that caught my attention, because I wanted the battery box and the electronics to look a bit like an air-cooled engine to keep the overall cafe racer feel, even though it would be electric. What I quickly found out was that this is an incredibly configurable and scalable CAN charger. It may be a bit overkill for what I'll be using it for, but the level of configurability means that the charge profile can be set perfectly for these pouch cells and significantly de-risk the charging. The terminal tabs were bent over each other to make series connections between each of the cells. I made up a bolt-on clamp design using some aluminium extrusions to secure each of the connections. Also, with the significant current output of these cells, I wanted to minimize the chance of terminal shorts, so I came up with an end cap and spacer solution that would provide some level of protection and help with cooling inside the housing. The spacers and end caps were 3D printed from Polymaker ASA, which needs to be printed at a bit over 240 degrees Celsius. The glass transition temperature, which is where the plastic starts to soften up, is around 100 degrees C, well outside the normal operating temperature for this battery. Also, because these parts aren't being mechanically loaded, they should remain effective, even if temperatures do exceed operating norms. In fact, thermal runaway is likely to occur before the plastic melts completely. The pack is made from 2 stacks of 12 cells arranged side by side. The bottom 2 cells were connected across the pack to make the series connection, and each cell terminal will have a balanced lead connected to the BMS. The battery pack will be a 24S, which means 24 individual cells connected in series for near enough to 100 volts when charged. The pack design I came up with uses aluminium flat bar to strap the cells together and extrusions on the top and the bottom to keep everything supported properly. The 3D printed spaces have depressions that lock into the aluminium flat bar and a center hole that takes an M4 threaded rod to lock it all together in the middle between the cells. I'll need to do some testing to see how this holds up on the bike. The end caps and spaces alternate, so the series connections can be stepped up to the next cell level at each end. Since these cells have a 74 amp hour capacity, I was able to get pretty close to my capacity target without having to run parallel banks, which was good because there wouldn't have been enough room in the frame. The challenge with using these cells was their size. The space in the lower part of the frame will be absolutely maxed out, so each level had to be staggered slightly to make this fit. I set the terminals up in the midsection of the pack with about 10mm of plastic shielding between the negative and positive terminal bolts. The reason I did this was because the pack will sit in the lower section of the frame and the outputs will be at the front of the bike where the frame rails get really close together. This seemed to be the most pragmatic layout for where everything needs to be mounted. The connections to the pack are made using an M8 bolt and secured with a nut using a socket from the top. The holes in the cover were carved out using a rotary file bit after the piece was printed. Once the battery was finished, it was time to start setting up the wiring. I'd had a bit of experience with 12-volt automotive stuff, but this was the first time I'd done anything with higher DC voltages. I'm pretty sure I overspec'd the main power leads from the battery, but that was to help minimize potential for heat in the pack once it was all sealed up. The high voltage lines between the battery and the motor controller used double O gauge, double insulated welding wire. The high voltage cables were all terminated with crimped I-terminals using this 12-ton hydraulic crimper. The battery, contactors, and motor controller all used terminal bolts. The terminals for the main battery connection were bent at right angles in a vise. After playing around with the layout, the best way I could come up with for routing the power was straight down into the primary pack fuse. I had to cut the fuse holder in half so I could make the assembly fit and also run the output back up to the top of the pack. The main contactor will sit somewhere above the battery at the front of the bike. At this point, I'm thinking about mounting the contactor sideways to simplify the connection from the battery. Having a decent wiring diagram has also been really helpful at this point. I used thinner gauges of the same type of wire for the charger input as well as the DC-DC converter. The orange sheath is another VSB14 requirement for any cables running more than 60 volts DC. I moved the main battery pack down to the build table to start wiring everything in for a bench test. The first step was to wire in the master control unit, then configure the battery pack and the controller parameters in the BMS so everything works correctly. At this point, I'd already tested that the BMS leads were connected properly. The BMS satellite on top of the battery pack uses an ISO SPI connection back to the master control unit through the yellow and orange twisted pair. The master control unit, or MCU, is basically a charge controller and a BMS controller in one. To get the MCU running, I connected the power through a small fuse block, then used the original key switch to turn everything on and off. The state of charge meter and the charger were initially connected on the same CAN bus using the blue and green twisted pair, but as I found out pretty quickly, both devices run on different baud rates. The fix was to run both devices on their own separate CAN channel at the correct boards. The MCU can be configured through USB using a terminal app like PuTTY. The first thing I did after powering everything on was to connect to the MCU, check the cell voltages and enable balance mode. The initial config went really smoothly as well thanks to the team at Thunderstruck. They helped spec a base config to suit the cells in my pack, so once the CAN board issue was sorted, the charger fired right up with the EVSE plugged in. But before plugging anything into charge, the battery needed to be wired in properly, so I got that and the motor controller finished because I was really keen to see that motor spin. everything wired in on the bench, ready to test. So we've got the positive and negative terminals on the battery. You can see the negative terminal runs straight up into the motor controller there. That's a direct connection. Then on the positive side, comes down through the main battery fuse. This is a 150 amp fuse. Goes back up through the current sensor and into the contactor. The contactor has a couple of takeoffs here. One of these, which is not connected, will run into the DC to DC converter. That's going to charge the 12 volt battery and the 12 volt subsystem. Then we've got this other lead, which is doubled onto here. This runs back through another fuse and then back into the battery charger output. On the negative terminal, I've got the negative lead going back to the battery charger. There's going to be one more negative lead that gets attached to this terminal. That'll just be for the DC-DC converter. The remainder of the motor control has also been wired in with what's necessary for the build. On this left-hand plug, we have the 3 leads that go to the throttle. On the right-hand side, on the second plug, there's the power, as well as the throttle interlock, which disables the motor controller when the system is charging. And there's also the brake switch, which enables the regenerative braking. So on the hub motor, we have 4 cables. We have the UVW channels, which are your main power inputs. We'll get to those in a minute. And then there's a 4th output here, which is actually a bundle of low voltage cables. And that runs back out here and plugs into the motor controller. So the beauty of the QS motor and Kelly controller kit is that the QS motor actually comes with 2 plugs. One of them is already pre-configured for the Kelly controller. So you basically just plug it in and all the Hall sensors are connected straight away. There's no fiddling around with it. It's worth mentioning it's quite critical that the motor controller's outputs are connected to the correct cables to drive the motor correctly. So each of these cables is connected to a particular winding within the motor, and these have to run in sequence. So if these are mixed up, then the motor controller is not engaging the correct windings in the right order, and your motor won't spin. So in order to reverse the direction of these motors, you actually have to do it from software within the controller. But these cables must be connected in the right way. On the motor controller, the outputs are marked U, V, and W. So to match these up with the QS motor, U is the yellow lead, V is the green lead, and W is the blue. Now, one last thing, the terminals on the end of the QS motor leads, they were actually a 6mm terminal, so they had 6mm holes. They just needed to be drilled out to 8mm because these are M8 bolts on the motor controller. So once they're drilled out, they bolt down perfectly fine and they work as they need to. This last little plug here is for the serial cable, and this is used to program the motor controller. So the serial cable only needs to be connected when you are doing the programming and configuration and can be disconnected after it's been set up. So this comes down to a pre-wired serial plug, which is then plugged into a serial to USB lead, and that gets picked up as a USB cable. The driver for the serial cable needs to be downloaded from the Unitech website and installed for the COM port to be recognized. The killer controller app called Motor ETS also needs to be downloaded and installed. The first thing to do here is to jump into the parameter config and make sure the motor properties, things like the number of poles and the Hall sensors, are correctly set. These were on the spec sheet, but were already set correctly in my controller. After that, the identification angle needs to be set to 170 for the controller to work out how to drive the motor. This needs to be written to the controller before a reset. When it's turned on again, the motor will jerk around a bit and then stop. Then it needs to be reset one more time and the identification angle will read 85 if the setup was successful. If the motor spins in the wrong direction, then the change direction tick box can be selected. In my controller, this was ticked and I had to actually untick it to make it spin in the right way. Next was the regenerative braking. This will be a bit of trial and error to get right once the bike is going, but for the time being, I added 10% for throttle off and 12% under braking. And finally, I set the max current to 35% because the controller has a 500 amp maximum rating. This should give about 175 amps, which is slightly over the 2C continuous discharge rating of the battery, but still under the 3C burst rating. I'll use this setting for testing and see how the battery performs. I decided to try the charger after everything was wired in and configured. It's on. After the initial CAN board cock-up was sorted, the whole charging and BMS platform just worked. Once the pack voltage was back into the 90s, I couldn't wait any longer and had to give this a try. I noticed that the default throttle setting felt a bit unresponsive. The dead zone was set to 20%, which made the acceleration feel a bit sluggish. I dropped this setting back to 5%, which seemed to do the trick. Once the wheels started spinning, I noticed inconsistent run out inside the rim. The outer radius where the tyre mounts looks okay, but the inside of the rim was not perfectly round and looked to be causing a bit of vibration on the table. Hopefully this can be adjusted out with balancing after the tyre is mounted. And that's it for today's episode. Thanks for watching. And don't forget, if you like the video, smash that like button and subscribe for updates. And here's a bit of a sneak peek into episode 4. We'll be looking at the 12-volt system. So wiring in all of the lights and the auxiliaries using the Motor Gadget Mo Unit Blue, wiring in the dash with the Motor Gadget Motorscope Pro, and the Vicor switch mode DC-DC converter. Awesome bit of gear.